For years, Europe bet hundreds of millions of euros on a brilliant idea: farming insects on an industrial scale to produce sustainable protein. Startups sprouted everywhere, investors opened their wallets, and pharaonic facilities multiplied. They were going to save the planet by replacing the soy that raises jungles and the fishmeal that empties oceans. Then the bankruptcies began. One after another, the companies that had promised to revolutionize food closed their doors. Billions evaporated. But here is the strange thing. The technology worked perfectly. The larvae grew, the systems operated, the protein was produced. The problem was not technical. It was something much more fundamental and simple. For years, the entire industry was obsessed with manufacturing expensive protein to compete with cheap products, while they completely ignored the true value of what they were creating. And that was the mistake that ended up costing them dearly. Welcome you to NovaGea, where we discuss the future. Today, we are going to explore together one of the strangest industrial transformations of the decade: how insect farms went from being the future of food to becoming the unexpected solution to a waste crisis that we didn't even know we had. To understand how we got here, you need to know an uncomfortable number: 77%. That is the percentage of all the planet's agricultural surface that livestock occupies. And here comes the part that hurts. All that land, all that water, all those resources only produce 18% of global calories and 37% of the proteins we consume. Meat production is, objectively, one of the most inefficient systems ever designed by humanity. Converting plants into meat always generates fewer calories than eating those plants directly. It is basic thermodynamics, and even so, we keep wanting meat and fish. Global demand for meat will increase by almost 48 million tons in the next decade. Ecosystems are at the limit, jungles are being razed to cultivate soy for feed, and we are emptying the oceans to make fish meal. We desperately needed an alternative. And then insect protein appeared with a proposal that seemed too good to be true. Insects occupy almost zero space, barely need water, grow at breakneck speed, and their nutritional composition far surpasses traditional sources of protein. And the best of all is that they feed on waste. Investors glimpsed the future and decided to open their wallets. Insect protein startups sprouted all over Europe, raising hundreds of millions of euros. The narrative was perfect: close the global protein gap, lower emissions, curb overfishing, and free up enormous extensions of land. Many companies copied the model of agri-food giants like Beyond Meat. They built massive, climate-controlled, technology-filled facilities designed to produce insect protein on an industrial scale. The plan was simple: replace soy and fish meal in animal feed, eventually enter pet food, and finally, human food. But then the disaster began. Competing with conventional feed in mature markets like Europe or the United States turned out to be a chimera from minute one. The first problem was getting clean organic waste. In Europe, the historical fear of diseases like mad cow or foot and mouth disease led to strict prohibitions. Any animal byproduct cannot be used to feed farm animals. And surprisingly, insects fall into that category. That means that any scrap that has touched meat, fish, or manure is banned for larvae destined for feed, even if science says there is no real risk. Add to that the costs of maintaining controlled climates in oversized facilities. All this made this protein cease to be competitive. It was basically the beginning of the end. The numbers did not lie, and they were devastating. In 2023, black soldier fly larva meal was sold in the European Union and United States at about $3,200 per ton. In other markets, it hovered around $1,600. Meanwhile, standard chicken meal cost $500 per ton. Fish meal, about $1,500, The difference was abysmal and unsustainable. The pharaonic plants that had been built with enormous capital investments faced a monumental slap when the real market numbers arrived. But here is the fascinating thing. Many pioneers aggravated the problem by making decisions that seem incomprehensible in retrospect. Some fed their larvae with virgin grain, perfectly edible, just to guarantee homogeneity in the final product. By obsessing over classic industrial parameters of consistency and standardization, they completely lost sight of the fundamental advantage they had. Insects, along with bacteria and fungi, are the planet's great recyclers. Their superpower is not just growing fast, it is transforming waste into valuable resources. Companies like Fly to Feed in the United Kingdom finally understood this and changed their approach radically. Instead of processing larvae until converting them into homogeneous meal, they began to commercialize live larvae directly to local poultry farms. The results were spectacular. Only 1.5% of the chicken's total diet was live black soldier fly larvae, and with only that amount, the growth of the chickens was accelerated by 8%. But to understand why this worked better, you need to see how one of these facilities really operates. The vast majority are black soldier fly farms, a species that has monopolized almost all the sector's attention. The reasons are practical. It eats practically any organic thing, does not transmit known diseases, is manageable due to its size, and has decades of research. The process is divided into 4 main blocks. First, waste pre-treatment. The organic scraps arrive at the plant, peels, rotten fruits, and spent grains from breweries. These are crushed until they form a wet paste that the larvae can easily absorb. Second, reproduction. There is an independent area dedicated to the complete cycle of the adult flies. They are given a premium diet, so they produce large and healthy eggs. They live in cages and are tricked with odors, so they deposit the eggs in wooden traps specially designed for it. Third, nursery and fattening. Every day those traps are collected, the eggs hatch, and the newborn larvae spend 5 or 6 days in nurseries. Around 2% of the best larvae are reserved to maintain the reproductive colony. The rest is automatically mixed with the waste paste in exact proportions. Fourth, controlled environment. The mixture of larvae and waste is transferred to trays in climate-controlled rooms at 27 degrees Celsius and 60% humidity. And here is the monumental technical challenge. Rarely do you manage a biomass that multiplies its weight by 5,000 in only 1 week. The metabolic heat and gases that these larvae generate forced the design of ventilation systems never before seen in other types of livestock farming. Daniel Taverner of Fly to Feed vividly remembers when he overloaded his boxes by mistake during the first days of operation. The larvae generated so much metabolic heat that the temperature rose from 28 to 40 degrees Celsius in a matter of hours. Thousands of larvae tried to escape the heat by desperately climbing up walls and ceiling. For him, it was a nightmare. Eliminating the ammonia and carbon dioxide they produce at an industrial scale is a completely different engineering challenge than any other type of agriculture. But once that problem is solved, we arrive at the final phase, the harvest, between 7 and 10 days later, when the larvae are in their 5th instar, which is their most nutritious moment. They are mechanically separated from the dry remains using giant sieves. On one side, you obtain the larvae, on the other, an incredibly rich, dry substrate that is worth gold as fertilizer. Oil can also be extracted for biofuels. Scaling these biological processes at an industrial level has not been easy precisely because you are raising complete living beings, not manufacturing a chemical product with controllable parameters. Each batch is slightly different. Environmental conditions fluctuate, and living organisms respond in unpredictable ways. But mastering this complexity turned out to be only the half of the equation. Larry Koch, executive director of Flybox, insists that rich countries should not obsess over selling protein. According to him, the industry is sleepwalking toward an absolutely monumental food waste crisis, and that same crisis can become the biggest opportunity ever seen for the sector. Governments are dramatically accelerating toward the circular economy and zero waste. Between 2025 and 2026, total prohibitions on disposing of organic matter in landfills will come into force in the European Union and the United Kingdom. In the United Kingdom, it is already mandatory to separate food scraps. That is why companies like Flybox are turning their business model 180 degrees. They stop seeing themselves as producers of protein and present themselves as waste managers via insects. They no longer compete with soy or fishmeal. They compete with anaerobic digestion plants. Today, most of the organics collected in Europe end up in digesters that produce biogas and fertilizer digestate. It is a mature and well-subsidized technology, but it has two fundamental weaknesses that open the door to the larvae. The first weakness is scale and transport. Digesters need gigantic plants to be profitable. Transporting waste with 70% water hundreds of kilometers is literally moving expensive water. The second weakness is the type of waste. Digesters want fat and oil. Fruits, vegetables, and grains yield little gas. With the avalanche of new mandatory waste, many digesters are simply not going to want them. The larvae, on the other hand, love precisely the watery and low-energy waste that digesters reject. This was the missing piece of the puzzle. The economics of a larvae plant changes radically according to where it is located. In rich countries, the dominant cost are energy for climate control and specialized labor. But by reducing 15 tons of wet waste to only 1 ton of concentrated product, the logistical saving is brutal. And the most important thing, someone is already paying to get rid of that waste. You are charging to solve a problem and, in the process, generating valuable products. That scheme changes completely in low-income regions. In Africa, China, and Southeast Asia, the regulatory hurdles on what waste you can use are minimal or non-existent. Furthermore, the tropical climate helps enormously by reducing climate control costs, and labor is much cheaper. Suddenly, the original protein factory model does work economically. There are companies in these markets that already sell larva meal at an approximate price of $1,000 per ton, competing head-to-head with fishmeal. In Thailand, there are perfect examples. They offer a protein that equals the quality of the world standard, but cheaper, and without even mentioning the word sustainable, because in those markets, the only thing that really matters is the price. The brutal irony is that in those countries, organic waste is worth nothing economically, because you can still simply throw it in a hole. But when the day arrives, and it will inevitably arrive, when they prohibit landfills, only about $10,000 will be needed to set up a larvae farm in polytunnels. That means that this will be the fastest and cheapest solution that will be available. The real environmental benefits of this technology are more important than what the majority imagines. In 2022, we already exceeded 1 billion tons of annual organic waste globally, and it is expected to grow another 50% in the next 25 years. This waste represents almost 10% of all global greenhouse emissions when it rots in landfills, releasing methane. The larvae close that cycle with a much lower carbon footprint. And although insect protein may have been oversold initially, its advantages are undeniable when you understand the complete system. The frass, which is the excrement plus the molted skin of the larvae, is a very complete fertilizer rich in nitrogen, phosphorus, potassium, and most fascinating, between 3 and 7% chitin. That chitin triggers the activation of natural defense mechanisms in plants. Plants produce more defensive enzymes and compounds that protect them against pathogens. Studies in tomato, lettuce, and strawberries show reductions of up to 70% in damage by nematodes with adequate doses of frass. Automation is also advancing, rapidly taking advantage of natural behaviors. The larvae self-harvest when they finish eating, naturally migrating out of the substrate. Mixed ecosystems are being explored with fungi, bacteria, or even algae working symbiotically with the larvae. The future is being built on the mistakes of the past. The story of insect farms teaches us something fundamental about innovation. Sometimes the most valuable product is not the one you thought you were creating. For years, the industry chased the dream, producing cheap protein that could replace soy and fish meal. They spent billions building pharaonic facilities for that objective, and they failed spectacularly. But in that failure, they discovered something potentially more valuable, an elegant biological solution for the organic waste crisis that is looming. In the coming years, we will see if the new European waste management laws finally catapult the sector toward massive economic viability. While the world discusses how much protein costs, a simple fly reminds us of the great lesson of the bioeconomy. The true value is not in extracting more resources from the planet, but in wasting less of what we already have. Insect farms are not the future of food. They are a future where everything that is left over is converted into something of value.